say, bold, net, canlı, hey, hey, say, test, say, hey, hey, 1, 2, 3, 4, say, hey, test, 1, 2, 3, 4, ses kontrol, nasıl? Nasıl yani?
Şimdi ses geliyor mu?
Kısık mı gidiyor, nasıl?
Hiç gelmiyor ses.
Hiç mi?
Hı.
Benim şimdi sesim gitmiyor mu? Sen bırak
Yok.
onu hemen bakalım. Hey, 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 hey,
Şu an geliyor mu?
hey, test, 1, 2,
Şimdi bu
3,
nasıl
4.
geliyor? Bu ses şu an konuştuğum nasıl geliyor size? Yani şu anda farklı bir mikrofonla konuşuyorum çünkü. Ha, kapatayım telefonu. Kapatayım. Siz kulaklık.
Hey, tamam yükselteceğim. Tamam.
Tamam.
Hey, hey, bir
Şimdi
baksın. Hey, hey,
mikrofondan
hey,
gelen ses bu. Benim konuştuğum. Tolga da kulaklıkla konuşuyor.
hey, 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 test,
Kulaklıktan
1,
gelen
2, 3. Yaka mikrofonu.
Yaka mikrofon iyi mi şu anda?
Hey, hey, elleme abi, ben başka bir şey bakıyorum. Hey, hey, test, hey, say, 1, 2, 3, 4. Ses kontrol, ses deneme, prova, 1, 2, 3, 4.
Düşük diyor Çiğdem Hanım.
Hala mı düşük?
Peki
Bir
şimdi
dakika
şu ses
abicim.
nasıl? Bu ses nasıl? Şu an konuştuğum nasıl size gelen ses? Bu el mikrofonu, diğeri yaka mikrofonu. Bu ses daha mı iyi? El
Şimdi nasılmış benim? Hey, 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 test.
mikrofonu düşük geliyor.
Tamam. 1, 2, 3, 4. Bir dakika abi, elleme. Elleme abi.
Tamam.
Hey, sen bir dakika, şimdi yaka mikrofonu tamam mı? Bitti mi?
Yaka mikrofonuyla
Hey, 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 test, 1, 2, 3, 4. Say. Hey, test, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, okey. Zaten 5 saniye sonra falan oraya gidiyor herhalde. Ve hatta daha fazla.
Şimdi ben konuşacağım. Kulaklığı takıyorsunuz herhalde. Ses test, ses deneme test. Test 1, ses 1 2 deneme test ses. Test ses deneme. Tolga konuşmuyor, ben konuşuyorum diğeriyle, el mikrofonuyla. O geçti, o biraz geç geliyor şimdi. Şimdi benimki daha yeni geldi. 7 saniye falan farklı geliyor ses internetten. Ses deneme test 1 2 3. Ses 1 ses deneme ses. Ses deneme 1 2.
Tolga seninki iyi geliyor biraz. Tamam. Şimdi seninki de iyi gider.
Tamam.
Bir dakika bak bakalım.
Tamam. Okey. Çok
Bir dakika.
teşekkürler. Bir saniye.
Şimdi yükselttik. Bülent'in konuştuğu el mikrofonundan ben konuşuyorum. Hey, 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 say, hey, test, 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 1, 2, 3, 4. Ses kontrol, ses deneme. Bekliyorum, buradan görüyorum zaten.
Tamam. Çok teşekkürler. Tamam.
Tamam mı?
Ne yaptın? Hepsini dibe mi vurdurdun?
Thank you for the very nice introduction, and thanks for coming. So today I'll try to talk about causal mechanistic pathway-based analysis of omic profiles. And I'll try to explain what I mean when it comes to causal and mechanistic. But I lead a team of very talented and young people, of 10 actually. 2 of them are just joined, so they're not on the slide. But pretty much everything I present are work of them. And a lot of the things that I present are done in collaboration with multiple universities across the United States. This is really a partial list, but this is these are the teams that I work with. I have a very long collaboration with Gary Bader at University of Toronto, and Chris Sander was my mentor at Sloan Kettering, and now he's in Dana-Farber. I still have a long-running collaboration with my PhD advisor, Uğur Doğrusöz, at Bilkent University, and I have some local collaborators at OHSU. And a lot of this work is supported by either NCI or NHGRI or DARPA grants. If you look at what is happening, especially in the cancer biology domain, I feel that a lot of it is data-driven biology with little mechanistic or causal explanation. And there are reasons for this. The primary cause is that biology as we know it is a reductionist science, right? You know, biologists are really good at looking at pairs, a very small relationship, isolated with positive and negative controls, show it in 5, 6 different ways. Yes, that this protein actually binds and phosphorylates that protein. And then that goes into a paper, it gets published, and this is just one piece of knowledge fragment, and then we have millions of those. Now, when you go to something like TCGA, the Cancer Genome Atlas, what is happening is that you have thousands of patients, and for each patient you have thousands of data points, right? There's no time whatsoever or no mechanisms to merge those data points with that all the little fragments of knowledge that we have in the literature that was established through decades of biology. So what happens is that you get all these high throughput profiles, you observe the correlations, more or less. You know, you can do fancy correlations like mutual information. They're still purely data-driven approaches. And then you will do some de novo inference, and you'll select the most interesting relationships. Sometimes you'll go back and test them in the lab, and then you'll publish storylines, and then the cycle goes on. This doesn't scale. Also, this is not predictive. If you try to get any of this information and try to apply this to a precision oncology setting, where you have patients and then you get these high throughput profiles and you try to figure out what kind of drug combinations will work for that patient, these storylines you'll quickly find out are very close to useless. Again, they have little predictive knowledge. So how can we go from here to something more mechanistic, more predictive? What I have been trying to do, and this is a little bit depressing to say, but I've been trying to do this for 20 years at this point, is I would like to replace that de novo inference with something more causal, some mechanistic. And I'll call this thing CellMap. And we'll talk a little bit about how to construct these things, okay? So in that mode, what you're doing is that when you have all these observed correlations, you're mapping this onto a big mechanistic model of what's going on inside a cell. And then now you can do an interactive pathways. The key thing here is that when you go back and perturb and validate, the artifact is not just another article, not another paper published, but incremental model improvement. Now this sounds a little bit of a dreamer talk, but I think we are actually moving towards that. There are many phases in clinical science, in oncology, that this is happening. And I'll try to explain what we are doing at OHSU. But once you have a mechanistic model like this, then what you can do is that you can get a profile from patient, and then you can map on these cell maps, and then you can determine active pathways. And this might be a path to personalized medicine or precision medicine, depending on which terminology you prefer. And this is something that we routinely do now at OHSU, and I'll try to explain how we go about doing this. So what does a cell map give you? So what do you get? The first thing that you get is mechanisms. You get explanations. You get why. And this is important because in a precision oncology setting, we're talking about late-stage metastatic cancer patients typically, and we want to find a particular combination that works for them. There's no time whatsoever to do a proper clinical trial, right? For example, in our own precision oncology trial, we have 50 drugs, and we typically will give patients combinations of 3. So we have thousands of possible drug combinations. There's no way whatsoever to even do a toxicology study on these. So how do you go from single drug data and these patient profiles to combinations of drugs? And there's one way to do this is if you have an access to the mechanism, right? You can do that. Now, most of the engineering fields will do this seamlessly. When you take your car to repair, your repairman does this seamless because they have a model of the car, they have a model of the chemical system that they are perturbing, or they have a model of the CPUs. So this type of mechanistic explanation is inherently established in engineering, but it really is not in biology. And again, there are reasons why, but we would like to move from what we are to that space. And also, it gives you surprising predictions, things that you didn't know about the mechanism. And I'll give you an example of this. Another thing that is not as well discussed, but it's equally important, is that in almost all fields of systems biology, we get killed by the size of the model space. For example, if you're inferring networks, right? Say that you're trying to infer a network of size 100. The space of all possible models is 2 to the 2 to the 100. Okay, it's gigantic. Now, any form of inference, you'll quickly find out that you are overfitting because your data will be invariably infinitesimally small compared to the model space. But if you can use priors to constrain the model space, to reduce the search space, then you get an option to do a precision recall trade-off. Okay, I'll try to give an example of what that is. And another important thing is that you now have a path to get better, because through incremental model improvement, you can now improve the model and improve your predictions in an iterative fashion. And I'll give an example of this as well. And when you're using priors, when you're using mechanisms, when you're using these cell maps, there are several things that you need to consider. One is level of detail. What level of detail do you want to operate on? And I'll give an example of this. The second part is coverage. How much of the biological system that you're modeling is covered by your knowledge base? Integration. How hard it is to bring different pieces of the model and then use them together. And context, which is, if you think about these fragments, at least for biological pathways, right? Two proteins might bind to each other in one context, and now you want to use it in a different context, which is, for example, in one cell type or one organ. Probably PIF3 binds to MDM2 in every cell in the same way, but probably this is not true for FGFR3. Okay, so you have to also consider all of these. Okay, so let's where do we get these models? So this is where I started 20 years ago. We started this little project called Patika, which is one of these pathway databases. I believe it is here. So I'm proud author of this 700 things. There are many, many pathway databases out there. I think this is a little bit outdated. I think we have 800 now. And all of these have their own different standards, all different formats. What they're doing is that they're reading the literature, and then they're curating the information in the literature in a computable format. Okay? Maybe you have used Keg, maybe you have used Reactome, but they're truly a big jungle out there. So one of our major accomplishments, and this was 10 years ago, was to establish a standard called BioPax and convince most of the major players in this field to export their data to BioPax. And then we built something called, the BioPax is essentially an extension of chemistry. There's nothing magical about it, although there are several interesting semantic issues. I'm not going to talk about those, but I can talk about those for 5 hours if you want to. So the major achievement out of this was that we got the major players in this field export to this format, and then we integrated these into this big database called Pathway Commons. This is an NHGRI resource. And it has, by the last count, has 420,000 biochemical reactions, all human, all hand-curated, at the level of phosphorylation sites, PTMs, complexes, subcellular localization, very, very detailed knowledge. 400 plus thousand biochemical reactions, 2-3 million protein interactions. And this is something that you can use. This is publicly available. We have web services, we have APIs, we have libraries for Python, for Java, for R. It's being widely used. We typically will get a couple of million hits per year to our web services. So my talk I will not talk about how we build this or how we are trying to expand this, but how we use this in conjunction of conjunction of omic data, and of particular focus is about multimodal omic data. So quick quiz. What do you think this is? German speakers in the audience, please don't spoil this for the rest of the audience. They are sewing patterns. So they used to be in this. They used to be the centerfolds of this fashion magazine. My mom used to have a couple of those. So I think it was 80s and maybe late 70s. Late 70s, yeah. And sorry. What's happening is that every single model in that magazine has a number, and then you get a piece of soap and a piece of fabric, and then you trace that particular line on the fabric, you cut it out, you sew it together, you get a skirt, you get a jacket. Yeah. So why am I showing this? Is because this Pathway Commons is a little bit like this. Okay, what we have done is that we gathered information that is curated across different cell types, across different perturbations, across different experimental conditions, and then we superimpose together. Okay, they're flattened. We flatten the context. Now, all of the algorithms that I will describe from this point on, the challenge is we're trying to inject the data, inject the profile, and then we try to reconstruct the subnetwork that is active in this particular context. Okay? So I'll try to give a few examples of this. And when I think about pathway analysis, I think in several different levels. And most of the literature out there will talk about gene sets. When people say pathway analysis, I won't be talking about that. Okay, that is relatively well-established system, but it is not causal. There is no grounding. It has its own issues. If you want me to hear, talk negatively about gene set and pathway analysis at that level, you can meet me after the talk. I can talk for a couple of hours. But I am more interested in this level 3, which is activity flow, where the network is A somehow activates B, or A binds to B, and then they do something together. And at the 4th and 5th level, which is a process network and quantitative network, now you have really biochemical models. Now you have mass balance reactions, you have stoichiometry, you can start doing fancy things like flux balance analysis or rule-based modeling, or at the quantitative network, you might start modeling these things with ODEs and PDEs. The problem with both of these levels is that they don't scale as well, and also you typically don't have the constants. So for example, for a reaction rate, you will need a reaction rate constant, but that constant might switch based on the salt concentration or the temperature by 2 to 3 orders of magnitude. So it is very difficult to generalize these models across contexts or to merge them. So I'll focus on this level, activity flow level, where the relationships are still not as well quantitatively defined, but they're causal and they're directed. Okay, so first application. This is an algorithm that we call mutex. And this is not a notion that we come up with, but if you look at something like TCGA, the Cancer Genome Atlas, and if you look at genes, sometimes you'll observe a relationship like this where every column here is a patient. So these things are called oncoprints. Every column here is a patient, and then every row is a gene. Okay, those blue squares are homozygous deletions, so you lost both copies of the gene in that patient. The red squares are copy number amplifications, and the green dots are mutations. So what you're seeing here is that the patients will either have CDKN2A mutations, or CDK4 amplifications, or RB1 mutations. Okay, but it is very rare to see these things overlap. Okay, this is not common. Okay, there's a statistical pattern here. And then the reason for the statistical pattern is 1 is enough. Now this is like a crime scene. In a crime scene, you'll sometimes see a door is broken or a lock is picked, but it's very rare to see both the door is broken and the lock is picked. It doesn't make sense, right? 1 is enough. And it's the same logic here, that the tumor cell needs just one type of mutation to unlock that particular mutation, which in this case is the control on the cell cycle. And people have come up with algorithms for finding this in a purely data-driven model. What we have observed is that a lot of these mutually exclusive relationships happen on the same pathway. Again, because they're controlling the same thing. Because then the idea is that, okay, can we do a graph search on our pathways where we are seeing mutually exclusive relationships that are controlling the same downstream process? Okay, so the example of this is here. The CDKN2A will inhibit CDK4. CDK4 will inhibit RB1. So they're more or less on the same pathway. The type of the relationship is a loss of function, a gain of function, a loss of function is compatible with what you're expecting. And this is a mechanistic explanation to the statistical relationship that we are observing. Okay, so are you still with me? And this is the flavor that I will be talking on for most of the rest of the talk. So you have what you are gaining here is that you're restricting the search space. Now the alternative of this is that you can look for every possible combination or every possible module. Okay, but then you have to do a multiple hypothesis testing correction. Okay, and you'll pay a much larger penalty. Now if you restrict yourself to the known pathways, you'll gain substantial statistical power, and you'll trade off some recall. Okay, so that is the ability to do this trade-off. It actually turns out to be fairly powerful. But perhaps more important is that when you find a module, you want an explanation why that you can go back and test in the lab. You have a falsifiable conjecture, okay? And if it is not true, then you can modify your model. So we have done this for, I mean, this is fairly automated. At this point, we have a Docker image. This is run routinely on the next TCGA, which is GDAN. We are a part of that project. And what we're essentially doing is that we have a statistical metric. I'm not talking about that metric. But you know, we have to modify it so that we can do this on rapidly on a graph search. And then what we're doing is that starting from each protein, we do a greedy search to its upstream, looking for a module that has statistically significant mutual exclusivity. So these are some of the modules that you're seeing. These are detected in TCGA breast. And again, this is something that you can go and run by yourself in any cohort of sufficient size. For example, this is one close-up. So PTEN and PIK3CA, these are very well-known proteins. I don't need to kind of, I don't need mutual exclusivity analysis to figure out what is going on between PTEN and PIK3CA. They both, one will remove a phosphate group from a PIP3, and then the other will add to the PIP3, so you expect them to kind of work against each other. But HUS1B is a very little known protein, and it's only mutated in 7 patients in TCGA breast cancer, okay? So that alone is not sufficient for us to think of this as a driver, cancer driver gene, okay? And in precision oncology setting, if we get a patient with a HUS1B mutation, that will definitely not register in our radar, okay? We will not think about this as something significant. This will not show up in our reports. There are hundreds of other genes that we will consider before it comes to HUS1B. But that statistical relationship is 10 to the minus 17, the p-value, after multiple hypothesis testing correction, okay? And turns out that HUS1B actually HUS1B deletion will have a very similar PIK3CA, PTEN-like effect on the CHEK1 and CHEK1 downstream, the downstream of the control. So, if you get a patient, we didn't get one yet, with a HUS1B deletion, our analysts will be armed with this algorithm to interpret this mutation correctly and maybe propose a PIK3CA inhibitor for these patients. Okay, this is the general idea. Okay, second application is something that we call causal path. And it revolves around phosphoproteomic data. Phosphoproteomic data was relatively rare, 5 years ago, but things have changed substantially. Now we have several different projects. CPTech is the largest one, and these projects produce routinely 5,000 to 6,000 phosphoprotein measurements per patient across tens and sometimes hundreds of patients, okay? And this data is becoming increasingly more common and more public. And for a lot of these, you will also have coordinated gene expression profiles and coordinated mutation data. So what we do is very simple. Okay, I'll explain something more sophisticated as my application 3, but this is really simple, really straightforward. What we're doing is that we get all these complex, detailed mechanistic processes, protein complex formations, moving from one subcellular location to another, post-translation modifications, transcriptional control. And from these, we have a library of BioPEX graph patterns to detect potentially causal relationships, okay? And then we create this causal binary graph. And then from there, we put in the phosphoproteomic data. Say you have ovarian cancer data set with 70 patients, 5,000 phosphoproteomic data each, so you can actually look at correlations between phosphoproteomic measurements across this cohort. And what it will do is that it will do a statistical evaluation on these relationships, okay? So for example, we know that in that data, NIC2 110 phosphorylations increased, and we know that this is an activating site. This is all coming from our background database. And we know that when NIC2 is phosphorylated, it will actually go and phosphorylate MAPK14. And in our data, MAPK14, that particular phosphorylation site, is also increased in correlation with the NIC2 110 increase. And that now becomes a little causal explanation. And what we do is we automatically scan for these things that we can explain across these 400,000 biochemical reactions, and then display this visually to our biological collaborators, okay? So for example, in this case, we have, I just wrote a letter to the editor for the paper, and we have 19 different collaborations on this because it is so easy. When we get the phosphoproteomic data, we just throw this thing at it, get those images sent back to our biological collaborators, and they're typically very happy. In this case, for example, this became a little paper recently. This was a platelet activation experiment, and then our collaborator found that although he knew that RTN4 was very important, he didn't know that there was a connection from the NIC2, MAPK14, and MAPK2 to that particular phosphorylation. And then he showed that by inhibiting this step and this step, he can actually turn off the platelet activation. So the causal relationship was real, and this became a little paper on its own. So, so this is the type of relationships that we can do, and we have done this on whole TCGA. So these are all the recurrent relationships that you can see across 10,000 cancers, and they're remarkably recurrent. Now, we don't see anything like this in gene expression data. And in gene expression data, all of these relationships are highly cancer specific. The lightest edge here means that they are recurrent in 13 different cancers. So that particular statistical relationship exists in 13 different cancers. The darker ones are 20 plus. So this is, in my mind, is the core cancer pathway that is determined by the RPPA. Of course, the caveat is that RPPA, which is an antibody-based platform, looks at 400 different relationships. But still, I find this very, very remarkable. This is another example. This is an EGF stimulation. This is now a time series data. You're seeing the time here, right? So 64 is losses. Now we are going to time 2 minutes. So you'll see this immediate boom around EGF, right? The pathway just lights up. And then what you're seeing is that a kind of a die-off period and some sort of long-term responders, okay? And we have several examples where we actually have that type of data, and then it is very, very straightforward to apply this method. Now, this box at the right is what we call the penalty box. These are the things that have changed significantly, but we have no explanations for them. And then the reason is that our pathway information is incomplete. Okay, and this is the trade-off that you're doing. My estimate is that we have 2 to 5% of the literature in pathway comments. And this is literature, not reality. Okay? You can still do amazing stuff, but I always dream about what we could have done if we have, at least a 50% of the literature. Okay, so something slightly more mathematically sophisticated, something more complicated. Okay, what we have done here is that we have one cell line, a melanoma cell line, and we are perturbing that melanoma cell line with pairs of drugs. Okay, in this case we have 12 drugs. We are doing all combinations. Some of the drugs didn't work, so we end up with 112 different combinations, and also the single agent readouts. And then again, we are using RPPA, which will measure for 400 phosphoprotein measurements after the perturbation. So these are post-perturbation readouts. And then what we do is that we have a belief propagation method. I will not talk about the math. This was published in eLife 2015. But really, this is not something extraordinary. This is a belief propagation derived system with some tweaks. One of the key innovations here is that we are injecting the pathway comments information of all the edges that we know into the system. So we are trying to infer the network that is responsible for, in this melanoma cell line, for responding to different drugs, but we are doing this by partially inferring some of the relationships from the data and then using the knowledge where we can. So the way to do this is that we inject this prior information into the regularization step, okay? The step that kind of forces the sparsity of the model. And then what we do is we do what we call decimation. We will stochastically fix one edge based on the probability of it is actually happening to 1, and then we'll update the remaining. And this way we'll actually generate not just one network, but thousands of networks, okay? And each of these networks are actually expressed as ordinary differential equation executable models. And what we can do then is that we can do in silico perturbation. We can ask, okay, if this is the network, okay, and this pair of drugs I haven't tried yet, or this 3 drugs, I haven't tried yet, can you tell me how the cell will react to this unknown, unforeseen perturbation? And what we do is, in that case, we are running all of these thousands of ODE models with that particular perturbation, and then use essentially an ensemble method for coming out with predictions. So this worked remarkably well. So let me be clear, the bar is very low here because in the network inference field, people didn't do much in terms of scalable models. People never went above 100 nodes, again, because of the model explosion, right? 2 to the 2 to the n is your model space. But this works actually, this scales reasonably well. We were able to, in follow-up studies, we were able to infer networks of hundreds of nodes. And it shows reasonable predictive accuracy. So we have a R value of, when it comes to proteins, we are doing much better. So these are cross-validation or holdout experiments. But another thing is that if you don't use prior information, your predictions will go down. But perhaps more importantly, if you do any sort of bootstrapping, if you do any sort of subsampling or introduce noise into your data, without prior information, your networks will change dramatically, okay? Which is a telltale sign of overfitting, which, as I told you, is a common problem for this type of work, right? Overfitting is always the bane for this thing. When you use the priors, your networks will stabilize. Now, I'm not saying that the networks that we inferred is actually the reality, right? But they're stable, so now you can test, and you can kind of find an iterative way to improve them, okay? Which I think is very, very important. I feel that without priors, we are completely unanchored. With priors, we have some anchors, and we can slowly get closer to the reality by using an iterative system. So these are 3 of the algorithms. We have 6 that were either published or in the process of being published. There are different flavors of this idea. That is, we will get large number of profiles. We will merge them with a large superimposed biochemical network, and then we'll look for statistical relationships that we can explain using those fragments. How do we use them? So one of the reasons that I recently moved to OHSU is that they have this really innovative precision oncology method, which is called SMART. And it really is an umbrella program for multiple trials. The gist of it is that we are profiling patients longitudinally, a small number of patients. So when I was back in Sloan Kettering, the numbers were 15,000, 30,000, right? Here we're talking about 40, 50, 100 for different trials. So very low numbers, but we are profiling patients longitudinally. Okay, so the patients come in, They'll get a combination therapy. And these are all relatively late-stage metastatic patients. And we will follow them. And at one point, when we figure out that the cancer is coming back, the tumor is coming back or not responding, we will actually do the profiling again. And then we will give them a different combination. Okay, and when I mean profiling, we do RNA sequencing, we do exome sequencing, we do cfDNA, we will do cyclic IF, which is a multiplex immunohistochemistry. We will do RPPA and several other methods. Okay. Yeah, I already talked about these. So every week we'll get a biopsy, we'll screen them, and then if the tumor is coming back, there will be a tumor biology review and a clinical tumor board, and then we'll come up with a different combination for these patients. So my team is tasked with getting all those information and then producing, we generate, for each patient we generate tens of images like this using the algorithms that I previously mentioned. And we will typically do comparisons before and after. Because we have longitudinal measurements on those patients. For the first patient, I think we have 5 different longitudinal time points at this point. And we are not getting any because her cancer really regressed, and we can't see anything. We can't sample. It's very bad for science. It's good for her. So we will get tens of images like this, these network inferences that are comparing before and after. What happened after we give the drug, and what happened, in the next longitudinal time points. And then there will be an analyst that produces something like this, because no offense intended, but clinicians are horrible at digesting these things. Okay, so we'll get tens of these, and then someone will actually end up with this. And here, what goes into this report is what are actionable. So we'll find a lot of things that have clinical relevance, but little clinical utility. I mean, if there's a p53 mutation, we won't show it, or we won't emphasize it because there's nothing that we can do about it. We don't have any drugs for that. But in the SMART trial, we have a list of 50 different drugs, and the emphasis is that which of these drugs are actually applicable to these pathway changes that we have seen. The other thing is corroboration. So if 2 or 3 or 4 different algorithms are kind of agreeing on the same thing, for example, in our first patient that I mentioned, we have seen a very clear switching event going from estrogen receptor to the androgen receptor, right? Androgen receptor is not something that you think in breast cancer, but we have good drugs for androgen receptor for prostate. So when we finally put her into the testosterone antagonists, she responded extremely well. And the beauty of this is that we know why that drug worked, because when we profiled her after the response, when there's still a little bit tumor, the AR downstream signature just went kind of down, and her tumor just disappeared in a matter of weeks. So that was a little kind of feel-good success story for us, and since then we actually had more successes, and I was very skeptical in the beginning that this will work. Now I'm feeling much better about it. And what we are doing is that we are building all of these, we are creating these drug neighborhoods. So each of our analysts will go through these drug neighborhoods for each patient, and then read the literature. If there's a surprising event, we'll look for those, and then come up with the final report. So the idea is that we are generating automatically a lot of inferred networks, and then there's a summary step which is manual that are done by a human curator. This is not patient data. I'm not allowed to show you patient data, but this is an example of what we can do. For example, this is a CDK1, CDK2 inhibitor before and after. This emulates the images that we see for patients. These are cell lines, MCF7 and A375. And what you're seeing is that, this is, I'm not sure if this is visible, but this is CDK1 and CDK2. And you're seeing this massive downstream kind of a down signaling. These blues are all decreased phosphorylation events. So CDK2 was going to phosphorylate those guys, but it has a decreased activating phosphorylation, which is correlated with the decreased phosphorylation for these proteins. Again, you see a very similar massive downstream for CDK2, and you start seeing these chains of events, right? So our analysts are seeing these large-scale mechanistic explanations and then summarizing them for the clinical tumor board. And we're trying to build a know-how around how to do this. Okay, so this is what we do. The problem is that what we do doesn't scale. For each patient, we'll typically spend something between $40,000 to $50,000 on analytes, and then we will spend at least 1 week per curator time. And this is just a pathway analysis. There's many other different steps that goes into that analysis. It is very expensive, very time consuming. And also, we need better pathways. We are still killed by our coverage. So our team also explores, I call this the nerdier part of our team, through 2 large DARPA projects. Can we use NLP? Can we use crowdsourcing? Can we use human-in-the-loop curation on demand systems? Think like Siri or Google Assistant. So this is something that we have built. So what you're seeing is that there's a Bob, which is our smart assistant. I don't know why we call it Bob, it just stick that way. And what you're doing here is that you're building a model by chatting with it. And what Bob can do is that it actually has the knowledge of TCGA, it has the knowledge of links, it has the knowledge of many, many different large-scale omic profiling studies. And as you're building the model, Bob can find these relationships and say that, hey, I know that you're interested in breast cancer, and in TCGA breast cancer data set, I found this correlation, and it's mutually exclusive, and then I found this paper that talks about the relationship. Do you want me to add this into your model? And Bob actually will add this. This is a part of a DARPA project called Communicating with Computers that we are building in collaboration with the Peter Sorger and his lab in Harvard. So you can do kind of a subcellular localization. It is still pretty cranky. There's a way to talk with Bob, and it doesn't understand everything, but we are actively working on it. So my dream is to take Bob to the clinical tumor boards. I want to have a Bob screen, because clinicians are great at clinicians are great at parsing tens of data points. They're horrible at, and unsurprisingly, parsing hundreds of thousands of data points. And this is where the clinical tumor boards are going, okay? And we will need assistance systems. We will, in the way we use, the Siri or Google Assistant daily, and we got used to it, we have to take these things to the clinic as well. So another flavor of this is that we have a human-in-the-loop system where there's a little kind of a chat room. People are collaboratively building models, because this is what happens in large-scale projects like TCGA. And one of the agents, one of the collaborators is our computer agent, Bob, and helps with the model building. We are also doing a version of this. These are the things that you can use today. They're publicly available. We have more advanced prototype versions of these. If you need help, please contact us. And a little extra. So the stuff that I talked about today is really, I'd say 30% of what we are doing. We spend a lot of time thinking about cancer early detection because we have this very large center called CEDAR that is led by Sadık Esener, another Turkish engineer. And then we also think a lot about precision medicine because of the SMART trial. that I mentioned. So there are questions about how are we going to model the cancer biomarkers to figure out when the patient is progressing, or in the case of early detection, how can we go from 98% precision to 99.9% precision? Because this is actually the level that you need to do proper early detection. In pancreatic cancer, say, pancreatic cancer happens in, I think, 7 to 8 patients in 100,000 people. So if you have a pancreatic cancer test that is 98% accurate, and we have one, by the way, that will say, that will turn positive for 2,000 patients. And only out of that 2,000, only 7 to 8 of them will have. So you're not going to go Whipple on 2,000 people, that's not possible. And you really cannot, do anything else with the pancreatic cancer. You typically won't see them in imaging. So what you're gonna do, you have to go to the 99.9% precision. And that's why the early detection is a very, very hard problem. So we have multiple algorithmic approaches, and we have a lot of resources that we are building within the OHSU computational biology program. So we have a Galaxy, we have a really good system for imaging. And we are getting increasingly into the imaging space. This is something that I haven't done, but now a big chunk of my lab is also working on this. And the key driver is that OHSU has again a center for imaging, which is called OCSSB, and they have several very fancy technologies. I'm going to just show you one. This is what we call cyclic IF. This is a multiplex immunohistochemistry system. What you're seeing is we can now do 10 cycles, and I think they just did 12 cycles of four markers, all co-registered on the same image. So you're getting essentially, almost 50 readouts per cell for 100,000 cells. So what you're seeing here is that we have automated image segmentation, which is surprisingly difficult. And once you have this data, you can really do fancy stuff. And what you're seeing is that cancer is a very heterogeneous, within the patient, heterogeneous disease. And when we sample just one metastatic site, we're actually missing a lot of the complexity. So this is something that we routinely do for all SMART patients. All precision oncology patients that I talked about will also get this. But this is not connected to the pathway analysis that we do. Right? This is essentially single cell proteomics. And a big chunk of, of our team also thinks about how to connect these things into the pathway-based analysis that we do, and how do we go from within cell modeling to between cell modeling. You can also look for which parts of the cancer. This is just I don't think this is useful, but this is just too fancy. And shameless plug. We have thanks to nice donation from Phil Knight of the Nike fame. We have a really nice night cancer building in OHSU, and we have multiple postdoctoral scientist positions open, and within a month or so we'll start recruiting 10 joint data science faculty with University of Oregon. And with that, I'll take questions. I'm not sure. I guess you have to shout. Yeah.
One thing that we are facing in daily life in the lab is reliability of all these pathway analysis in the web. In my experience, half of the proteins
Yeah, of the literature, depending on how you count. Yeah, yeah.
So, do you think the combination of all these methods will cover all the will be able to cover one day? Will create all this map for different cell types and different cancer types? Or is it so dynamic that, because in the last picture you showed that every cell has different signaling pathway?
Yeah.
Will we catch it one day, or will it be just turning around in circles?
It is definitely technically possible to cover 100% of the literature. It's just a matter of will and resources, and also, you know, some increase in the efficiency, because the gold standard in pathway curation is Reactome. I work with all of these pathway databases. Don't tell them that I have a favorite son, but Reactome is my favorite son. And they will cost $1,000 per reaction to curate to NIH. This is the cost. Now, we just got a grant to reduce. We just got a grant to reduce that to $10 with NLP. We'll be working on this. If we can even reduce it to $100, I think you'll see an order of magnitude increase in what is available. Another thing that we're trying to do is that we have this pilot project called Factoid. Horrible name, but this is again what got stuck. So what we're trying to do there is that, and this is our evil plan to take over the world. There will be a little checkbox during the paper submission process, and that says this paper contains pathway information, and then the author will be directed into a Bob-like system where it will automatically extract everything in that paper and then ask the author, is this what you mean? And then the author will be able to curate. We call this micro-curation. And then this will deposit it together with the paper. Now, it is not a crazy idea. This is what the protein structure community is doing. This is what the genomic community started doing, right? So it is not a crazy idea. Again, it's just a matter of execution and will and resources. I'm not sure if it will be successful. We're trying. But with some mixture of NLP and crowdsourcing, I think we'll see efficiency gains. And if there's will, I think we'll have much larger pathway databases. A lot of the stuff that we do works because the coverage around cancer pathways are much better than everything else. If you try to do our approaches, say, for developmental biology or for another organism, it won't work. There's just not enough coverage. But this is something that we struggle daily. So, yeah. Yes?
Alternative splicing and alternative forms. You completely ignore them.
And also microRNAs, right? I mean, these are things that depresses me to no end. Yeah. Yes. Any other questions? Okay, we can talk about the rest. Thank you.